Hello, I'm Professor Bill Buchanan, and I run a podcast series on world leaders in cryptography. And I'm so happy to have Yuriy Polyakov with me today. Hi, Yuri.
Yeah, thank you for having me, Bill.
So Yuri is the Vice President of Cryptography and a principal scientist at Duality Technologies. His research interests includes applied lattice-based cryptography, fully homomorphic encryption, and privacy-preserving machine learning. He's also a co-founder of the open source PALISADE homomorphic encryption software library and is a co-founder and project lead for OpenFHE. So, what's your current role and what does a typical day involve for you?
Yeah, so the current role, so I lead the cryptography team at Duality, and we have a hybrid schedule. So 2 days in the office and 3 days remotely. The days that are in the office, a lot of meetings with other researchers, with customers, and lots of meetings. And during the other days, I get to do some of the individual contributor work and some research, and yeah, it's fun. It's always something new, always exciting.
Yeah, it's good to keep the technical balance, well, obviously with the managerial leadership. And I think it's always important, even for a leader, to keep their technical skills and to keep reading research papers, because obviously to lead, you need to understand the state of the art. So, what were your school days like? Can you remember at school?
Yeah, it's actually quite tricky. Because yes, I do have many different degrees. So, for instance, master's in computer science, PhD in chemical engineering, doctor of science in physics and mathematics, and I actually worked in cryptography. Uh, uh, despite the many degrees, I think my education comes from home. So, and I'll explain a little bit more. So I was born and raised in Soviet Union, and my dad used to work for the Soviet, essentially, space system. So he worked on the life support systems for the Salyut space station and later for the Mir space station. And uh, I would say when the Soviet Union collapsed in 91, so my dad was a head of a research lab at the time, and he had to change his occupation. So he became a translator from Russian into English of scientific journals, and he started working from home. And this was like 92, 93. And we had a lot of interactions with my dad about various topics, be it history, be it foreign languages, be it research. And we had a lot of researchers coming to our home, and we had discussions, and that influenced a lot. So, for instance, I was taught from the very early, I would say, high school or middle school days to study topics on my own. And I was reading advanced physics or advanced math, college level math when I was in early years of high school, interacted with scientists, and started doing research when I was a senior at the high school. So my first paper got published when I was a first year student. So that influenced a lot. So those interactions, and then uh, I would say the next few years when I got my many of my degrees were quite interesting. We immigrated from Russia to the United States in 98. So I was a first year student at the time. And then after moving to the States, I was in parallel working in the information technology field as building wireless, one of the first wireless ISPs, building an e-commerce site that would at that time compete with Amazon, and in parallel was doing my studies, so bachelor and master's, and I got my PhD and Doctor of Science from Moscow. So I did some travel also. So it's I would say a lot was influenced by the interactions with my dad. And then later, I worked with other researchers in various fields, in physics, in chemical engineering, in cryptography. And these are my school days. So I would say I like to explore new things, to teach myself new topics.
That's great. Yeah, yeah. That desire to learn new things is obviously very important, and you obviously have a love for mathematics. So where did the spark for cryptography happen?
Okay, so initially there was a spark for math. So and that came about again from the interactions with my dad and other researchers. So a lot of my prior work was heavy in math. For instance, in chemical engineering, I was considered a theorist. Where it shifted to cryptography, I would say the main event happened in 2014 when I met Kurt Rohlhoff, who was a new professor at New Jersey Institute of Technology. I was also teaching at New Jersey Institute of Technology at the time. So although I had broad interest in cryptography, security, and worked in the information technology field, but when I heard about fully homomorphic encryption, and Kurt knows how to describe it well, then that's an interesting topic. It's very new. It's an emerging field. I got interested, and since then, that was almost 10 years ago, we started collaborating and working together, and here we are.
That's great because there's obviously some famous people involved, co-founders in the company. We have Shafi and Vinod from MIT. So it's quite a team that's been created. So what's the core focus of Duality as a company?
The core focus of Duality is on secure collaboration, typically between multiple organizations, or we can think of it multiple data owners. These different organizations want to work together on the data. The data has to be encrypted. They cannot share the data with each other. And they want to do analysis of the data. They build machine learning model or do private database queries. And Duality is building those solutions. And some of the technologies that we use are, may include not just FHE, but for instance, we've done some things with MPC, we've done some things with federated learning, with the trusted execution environment. So we often use a mix of technologies, a hybrid solution, to achieve that goal of secure collaboration.
Yeah, agree. And there's no one magic bullet in this. Every application is different. Every domain is different. Every instance of an application is different. I think it needs to be engineered, and that's the problem. Is that some people just think there's a one size fits all for all of these things, especially for information sharing. It's a very complex entity. There's lots of ownerships and rights that needs to be defined there. So, what's the history of the PALISADE library and how has it developed into OpenFHE?
Yes, so I briefly mentioned I would say, inception point
Mm.
when Kurt and I met in 2014. And I got interested in lattice-based cryptography, and Kurt was finishing on a project, so DARPA project, at the time, that first DARPA project that essentially funded FHE, the development of many schemes that we saw. And we started working together, and there was a new big program, 4-year program, DARPA Safeware, that Kurt was a performer of. The focus of that program was on program obfuscation using lattice-based cryptography. So we started, and the team that we were on there was called PALISADE. And as part of this team, we developed many lattice-based primitives, and FHE was just one of them in that project. And the main goal was to develop a program obfuscation capability. And so we developed digital signatures, attribute-based encryption, identity-based encryption capabilities. And this earlier project, PALISADE project, was, I would say, the focus was on lattice-based cryptography, so more broader focus than just fully homomorphic encryption, in contrast to OpenFHE, which later we launched as a project that specifically targets FHE. So this is, I would say, this DARPA program, DARPA Safeware program, gave a very big boost and took the PALISADE library from its early days to an open source library that was made publicly available in 2017.
Yeah, that's great. And I know it's quite difficult, and you have a long track record of publishing papers from your chemical engineering time into cryptography. What paper would you say was your best, and why?
Yeah, it's a very interesting question. Several papers come to mind. For instance, had an interesting paper in astronomy related to black holes and emission of X-rays from there, and some other papers related, for example, to the space technology and applying the life support systems experience to hot deserts. And there were a couple of different papers, of course, in chemical engineering, but I would like to highlight a very, very recent paper, the one that appeared on the ePrint yesterday. I think
Ah,
it's
yesterday. It's always the most favorite one is the one you've just published.
yeah, this one is, at least maybe it's because it's very close. But I think this paper may be a significant advance in FHE. And
Hmm.
the high-level idea is that we have two kinds of schemes which have their own advantages and disadvantages. And one of such families is the TFHE,
Hmm.
FHEW schemes, so
Hmm.
DMCGGI, and those are, I would say, very powerful. You can evaluate any circuit without any restrictions, but typically their main issue is efficiency. When the main capability that allows them to essentially perform an arbitrary computation is functional programming or functional bootstrapping or programmable bootstrapping, but this bootstrapping is done one number at a time. So and this is causes efficiency issues, essentially, when we need to work with a large data set. And there is, on the opposite end, there is a scheme called CKKS, so approximate homomorphic encryption, which is which can, I would say, bootstrap many thousands numbers at once, supporting this vectorized format. It's very efficient, but it cannot support certain kinds of functions, discontinuous functions, such as comparisons. They're very challenging. It can only support polynomial arithmetic. So what we're proposing in this paper, a solution to do this functional bootstrapping using CKKS. So we developed a method and actually a theory behind it and implementation that allows one to, in CKKS, to evaluate any function and get amortized time that's orders of magnitude better than this approach DMCGGI.
That's amazing. That's fantastic because you're right. The arbitrary circuit evaluation can be very slow and inefficient. And obviously, if we could use the CKKS method to be able to create any function that we want, then it would obviously make it much faster. So I look forward to reading that paper. That's absolutely amazing. So can you explain to our listeners roughly how homomorphic encryption works with these lattices and errors and noise and things like that?
Sure. So the concept is of homomorphic encryption is we want to be able to analyze data, encrypted data, and perform various kinds of analysis, be it machine learning or others, without ever decrypting this data. So we get essentially something that's encrypted. We want to compute a function or we do some kind of analysis. And with typical cryptography technologies, one has to first decrypt and so trust to someone who can decrypt, run this computation analysis, and then re-encrypt and send it further. The technology that we're developing, fully homomorphic encryption, does not require that trust, that the computation can be done by an untrusted host. So this analysis can be done you can share the encrypted result with someone else that has powerful computation capabilities. It can be run there, and the result of this encrypted computation would look the same way as if this party that did the computation had access to the actual data. And so it's like it changes the traditional model of cryptography, where we can talk about encryption only in transit or only but without being able to do anything to analyze the data. Here we're extending this domain that you can actually do analysis. You can do joint computations like the collaboration scenarios that I mentioned without seeing the data of the other person. So this is the most powerful, I would say. I mean, it's a very powerful capability. What is behind it? So all common FHE schemes are based on lattice problems, and a specific instance, I would say, that we commonly refer to is learning with errors problem, or ring learning with errors. And simply speaking, we know that if we have a linear system of equations, and in this case there it's a high dimensional linear system of equations, we can always solve it. I mean, they're simple solvers. As soon as we add to a linear system of equations a noise term, which we typically add as a Gaussian distribution, error distribution, and make this a noisy linear system of equations, finding a solution to such problem becomes very, very difficult, computationally hard, and of course it depends on the dimension of this linear system. And this is the high-level idea. So we introduce this noise to make a noisy linear system of equations, which is computationally hard. Of course, this noise helps with security, but may not help with efficiency, which I'm sure something will come up in our further discussion.
Yeah. And so with our lattice cryptography, we have this massive lattice of points with multi dimensions, and we take our vector and we convert that into a polynomial value, and then we'll create our matrix multiplications and so on, and then we can reverse them all back. Just like any cryptography, you have a way of scrambling it, and then all you have to do is unscramble it in the reverse order that you did before. But the problem that we have is that obviously you have a little bit of noise in there, and when you're doing multiplication, say, of polynomials, then that error is going to multiply up. So we have the concept of bootstrapping as an important concept in homomorphic encryption. Could you just explain what bootstrapping is and why it's so important?
Sure. So we introduce noise for security. So every time we encrypt data, or let's say a vector of data, there is noise. As you mentioned, Bill, every time we multiply, let's say, two polynomials with noise, the noise will grow and essentially quadratically grow. And if we keep continuing computations, this noise will keep growing and growing. And at a certain point, this noise will enter the area where the data is. So initially, the data and noise are separated from each other. But as more computations are performed, the noise gets bigger, and at a certain point leaves no room and starts mixing with the data. And of course, as soon as that happens, the result of decryption is no longer valid. So what's bootstrapping, the procedure proposed by Craig Gentry in his work from 2008, and it was published in 2009, is the procedure that allows one to reset the level of noise after a certain number of computations to a much smaller level, so that more computations can be performed. And so it's effectively, you can think of it as refreshing the noise, so resetting the noise to something much smaller. How much smaller, that depends on the, I would say, the complexity of the decryption circuit. So under the hood, bootstrapping evaluates homomorphically the decryption circuit so that it does do decryption, but it does it in a homomorphic fashion. And that is by itself a homomorphic computation. And so it has a certain noise associated with it, but the noise associated with bootstrapping is much smaller than the noise that the input ciphertext had.
That's great, yeah. And obviously, homomorphic encryption can either use a public key, so you create your key pair, public key encrypts, and then the private key can decrypt. And we can also use symmetric key. We can use the same key on either side, which isn't quite as secure. But for the bootstrapping, the key is an encrypted version of the private key that we use to clean up the noise.
Yeah, so it's always encrypted. That's the high-level idea. One way to think about bootstrapping is we evaluate the decryption circuit, which which is actually that decryption is quite simple in the schemes that we're discussing. It's just a linear function. But when we evaluate the decryption, we don't have access to the secret key itself. We have access to encryption of the secret key under either some other key or the same key. It depends on the setting. But that's exactly the idea. So we have to work with a decryption function where the secret key is encrypted, and that's why it becomes a homomorphic computation. The party performing bootstrapping never gets access to the underlying secret key, which is the basis of this.
That's great, because the times that it's taken for the bootstrapping is generally fallen massively. I think under a second was a recent paper. So obviously that's a major advancement in homomorphic encryption. Just that bootstrapping process is just becoming so much quicker now. So what do you think are the core use cases? Obviously, Duality has certain customers and they work in some domains, so you can't tell us about all the customers that you work with, but where do you think the core use cases? Because this exists as a technology and it will only become alive when we find applications that people and businesses find interesting. So where do you think the core killer apps are going to be for homomorphic encryption?
Yeah, I would like to maybe highlight three major kinds of use cases, or we can call them maybe application domains. The first one is a private database query, and I'll describe it in more detail. The second one is machine learning, privacy-preserving machine learning. And the third one is the use of FHE for various confidentiality purposes in blockchain. So these are the three major, I would say, application threads that are being explored. So I would say the most mature one in my mind at the moment, and the one that Duality is focusing on, is the private database query solution. So you can think of secure investigations, for instance, to want to perform a background check without revealing any information on who you are asking about. So it's a very simple example. So there are quite a few use cases around secure investigation. And the FHE, I would say, solutions are very mature in my mind and efficient for these problems. Then the area of machine learning looks very, very promising, but many problems in machine learning or AI often require multiple uses of bootstrapping. So they require, they typically work with so-called deep circuits or deep computations. And I would say the efficiency of those on regular CPU systems is still not always practical. And this is why there is a lot of effort that's being put into hardware acceleration, specifically for this machine learning applications and of the bootstrapping operation. So the blockchain, I would say, thread, which Duality is less involved in. So I would say that we're primarily focusing on private data query and the machine learning looks very interesting, and often for smart contracts in some other scenarios, solutions that can do things like comparison, etc., are of interest. So it's in my opinion, it's a relatively new application domain that's getting quite a bit of interest as well. But these are the three major areas with that look promising from the commercialization perspective in my mind.
Yeah, because a ZK snark just boils down to a circuit that you're implementing, like an electronic circuit. And obviously the FHEW can implement that. Obviously, if we can overcome some of the performance issues, we could implement any circuit that we wanted for a zero knowledge proof in a full homomorphic encryption infrastructure. So you've talked about the drawbacks. Obviously, the performance issue is a major thing. So how do you think we're going to address this? Obviously, GPUs are playing a big role just now in machine learning. So almost like we're moving away from the von Neumann CPU, horrible architecture, 64 bits and fetch execute, towards something that looks more like a computational mathematical engine like you would have in a GPU. So how do you think that's going to evolve over the next few years as we change this architecture and hardware?
Yeah, so I see maybe a couple of let's say I have a couple of comments. One is I do see similarities between the AI requirements and how we need this more powerful, let's say, GPU-based systems for more advanced transformer-based AI applications. Similar approach is, of course, being explored for FHE. So this is FHE requires, it has often compute-bound technology, and we need similar solutions. And also, we often work with large, I would say, data sets, just like AI. So similar challenges come into play. So I would say, from my personal perspective, the hardware acceleration of FHE bootstrapping is very important to support machine learning applications. And there are several efforts that are currently in progress. Some of them are GPU-based, some of them are FPGA-based, some of them are ASIC-based. And for instance, Duality has been a performer in the DARPA DEPRIVE program, and we're in the third phase of that program, building a special ASIC targeting, in this particular case, the CKKS scheme that I mentioned earlier, which we expect to give a speed up of, let's say, 3 orders of magnitude compared to CPU solutions. And with that speed up, we believe that many applications can become practical.
Yeah, that's excellent. And so we've been through various generations of homomorphic encryption. Craig Gentry obviously did the core work, but then we saw BGV and BFV, and then we advanced to CKKS and then FHEW on from there. So can you give us an overview of roughly what these methods do?
Sure. Yeah. So the very first proposal, and like again, the use of the word generation is can be misleading
Yeah.
sometimes. But let's say the initial class was Craig Gentry's scheme, and there was also an implementation of the early scheme that was made by Craig Gentry and Shai Halevi. It was a great proof of concept. It could do something, but it was far from being efficient for anything. So it was just a proof of concept of the idea proposed in Craig Gentry's thesis. So I would say first, in my mind, quite practical solution was developed as I would say what we call as BGV and BFV fully homomorphic encryption systems. This was around 2012 to 2011. So this is the timeline of those schemes. Many of them actually were developed as part of DARPA PROCEED program, the one that I mentioned at the very beginning. And those schemes, BGV and BFE, are great for, I would say, small integer arithmetic or finite field arithmetic. So they can do computations, modular computations, as long as that's what the intent is, to do either modular computations, or the numbers that we work with do not wrap around the modulus. And just to give an example, the database query solution that I mentioned, for example, what Duality does, or recent announcement by Apple of a solution that they suggest, they are based on BFE or BGV, so on this family. So this family is still being used, although, I mean, of course, these schemes were optimized in many ways. And typically, these schemes are used in scenarios where bootstrapping is not called. So they're used for so-called shallow computations. And many of these database query solutions, private query solutions, are like that. They work with shallow computation. So this is finite field. Then the next major thing was this FHE I mean, few, TFHE, sometimes called DM, CGGI, this family. The original concepts were proposed by Leo Deca and Daniela Michancho in 2015. The biggest contribution of that work was low latency for bootstrapping. And Tibiel mentioned that it was the first time when they were able to run bootstrapping in less than a second. And it's a very interesting design, because what they propose there is actually a hybrid crypto system. So it's not a one scheme like BGV BFE or Gentry's original design, but it's a hybrid scheme. You use one scheme as the input. So in this case, just a linear scheme, a partially homomorphic scheme. And then a different scheme is used for the bootstrapping operation. So it's RingGSW is a scheme that's used there. And this blueprint of, was proposed, actually functional bootstrapping is something that was enabled by this proposal, that in addition to bootstrapping, refreshing the noise, one could evaluate an arbitrary function. So which is, it's a extended definition of bootstrapping. So that was a big advance. The challenge, this approach allows executing an arbitrary circuit. The biggest issue is efficiency, because this kind of functional bootstrapping has to be done for each number separately. And then probably the most interesting milestone after that, sometimes it's called fourth generation, but one could argue that it's just a flavor of BGV BFE. That's called the CTTS scheme, so approximate homomorphic encryption. And that scheme is great for operations with real numbers or complex numbers. Often in practice, we use real numbers. Many of the machine learning advances that we have seen, such as logistic regression training or CNN inference or training solutions, are based on this very efficient CTTS scheme. So these are, maybe to summarize, BGV BFE are great for small integer arithmetic when we work with vectors of numbers. CTTS is great for working with vectors of real numbers. This DM FHW TFHE approach gives us an arbitrary computation capability, for instance, by evaluating Boolean circuits or some other circuits. But it's not as efficient as the other two.
Yeah. When I did electrical engineering, I did Chebyshev filters, as I remember. And I didn't quite see the scope of what he did as a scientist. And I think Chebyshev filters are really great within homomorphic encryption. And I know that you've embedded them into the library. So could you explain roughly what a Chebyshev function does in homomorphic encryption?
Sure. At a very high level, So this is mostly relevant in the context of the CKTS scheme, so
Yes.
a real number, the scheme that works with real numbers. The distinctive advantage of that scheme is that it can evaluate large degree polynomials very efficiently. And these polynomials typically work with real numbers. Another interesting result, I mean, that we know from just mathematics, is that many functions can be approximated or using polynomials. And I would say the most common method, or at least in fully homomorphic encryption, it's considered as the most common interpolation method, is Chebyshev interpolation, because it has very nice properties that if we want to approximate what's typically called a relatively smooth function, so the function, not discontinuous function, but the function that has some smoothness to it, Chebyshev interpolation gives us, I would say, the minimum error with the minimum degree of polynomial. There are some even optimality, essentially, properties that the Chebyshev interpolation has. So in, let's say, in the OpenFHE library, we provide a capability that one can give a function as an input, and then OpenFHE will find coefficients for the Chebyshev interpolation, Chebyshev series, and then the Chebyshev series can be efficiently evaluated inside OpenFHE. So this is a tool, but one maybe limitation of this tool is that the function has to be relatively smooth. It has to be within a certain interval. If we go outside the interval, effectively, there is so-called Gibbs phenomenon that it will blow up. The correctness will be lost. And this is why this approach of functional bootstrapping can complement it. So in situations when we want to essentially describe a discontinuous function that has discontinuity, we could use a lookup table approach. And that's what that functional bootstrapping provides. So it's something that would complement the polynomial approximation method.
Yeah, because I like how you've created the library. I can take a standard C++ maths methods like square root or square or something like that, and you can just easily convert that into the polynomial form. It makes it so simple to be able to implement these math functions. So another thing that you implement within your infrastructure is proxy re-encryption. Can you explain how it works and what you think the core use cases will be for that?
Yeah, sure. The proxy re-encryption that's implemented actually stems from some capabilities that FHE schemes provide. So there is a so-called key switching capability that's very important for multiplication, rotations in a number of schemes. And that same engine, key switching engine, can be used for something else. That something else is to switch a ciphertext from one secret key to another secret key without ever revealing any of those secret keys, using only a certain public re-encryption key. This is so it's the notion of key switching that's used here, where this particular technology, I would say, is promising, or where it can be applied. Publish subscribe systems. Let's say we either perform an FHE computation or we just simply send some encrypted data, and we then want to delegate the decryption to some other party that has a different secret key. And in publish subscribe system, this is quite common. The publisher may not know who's ultimately going to decrypt the result, and there should be a mechanism set up to switch the ciphertext from one key to another, so that uncoupling the knowledge of the publisher from the subscriber. And proxy re-encryption, in this case implemented using lattices, it's an extension of FHE schemes, can be used for that purpose. So simply speaking, it's a delegation capability, secure delegation capability to enable decryption of, let's say, some ciphertext by a party that the encryptor doesn't know about. at the time of encryption. This is the probably simplest way to describe it.
That's great. And I know within your library, you implement neural networks where you take a vector and you can cipher it with the public homomorphic public key. Then you've got your matrix multiplications, and then in the last stage, you can actually just apply the private key to be able to decrypt. So how do you see privacy-aware machine learning developing with homomorphic encryption?
Yeah, there are different, I would say, use cases and scenarios for that. So in some scenarios, we want to encrypt the data, put it somewhere else, and let's say run something like a training protocol and over that encrypted data. And in those scenarios, we deal with a neural network problem where both, let's say, data and maybe intermediate model are encrypted. And it's in the case of collaboration, when we have multiple data providers, this approach can be very useful. This is one scenario. Another scenario could be when the data owner itself, so the one that has access to the data, performs the computation. So let's say there is some encrypted I don't know, vector comes in, and the data owner has access to its own data in the clear. In FHE, there is a very nice property that if one, let's say, does a multiplication of ciphertext and plaintext, the result will also be a ciphertext. Anything that the ciphertext touches will get encrypted. So in these scenarios, when the data owner performs, let's say, computation, is involved in the model training or some other problem, FHE can also be used. So I would distinguish first, is the data encrypted or is the data in the clear? And that's one scenario. The same can be applied to the weights. Are the weights encrypted or are the weights in the clear? And FHE gives us flexibility. So it often depends on the use case. What is the use case? Is the use case of that multiple data owners encrypted data and put it somewhere, or is the use case where we can actually have a data owner involved in the computation? So this is like, these are the different trade-offs that I see, and of course, which particular use case works best for which problem. I mean, suits the best which problem. That's a separate question.
Yeah. I mean, obviously, the protection of the model is going to become extremely key for intellectual property development, but obviously, adversaries could get the Meta Llama model or OpenAI's model and change it in some way. So it sounds like the encrypted model looks to be interesting. I must admit, I've only investigated the data being encrypted. I haven't looked at the encryption of the model. So I think that's obviously an interesting area of research overall.
Yeah, maybe I'll even mention that another application. So in my prior discussion, I focused on the training problem. There's also an inference problem, which is typically much easier. So you have an encrypted model, and you need to do inference on the data that you have. It could be linear regression, could be logistic, could be neural network inference. And in that setting, often the model is encrypted. I mean, the data can be too. I mean, and this inference problem is actually much more tractable practically. So it's often does not require very deep computation. So it can be efficiently solved for many scenarios using current FHE capability. So the problem, like the model was already computed somewhere using some process, and we're just using it for inference or classification, regression. So this is an important use case that comes up.
That's great. So we're moving away from a role-based approach to cybersecurity, very much towards a zero trust type environment where we need to define the attributes for every data element almost. So do you think there's a place for attribute-based encryption within a homomorphic encryption infrastructure?
Absolutely. Yes, there is. And actually, as part of this Safeware project that I mentioned earlier, DARPA Safeware, when we developed the original PALISADE, we actually built attribute-based encryption capabilities, ciphertext policy ones and key policy ones. So there are two different flavors of attribute-based encryption. They are very useful. I would look at them as further extensions of the proxy encryption concept that I mentioned earlier. There you have to have the input key and the output key and have some process of converting between the keys. Attribute-based encryption is a more general capability, which, based on certain attributes, decryption can be allowed, for instance, or not. Also, attribute-based encryption can be combined with FHE. I mean, it can also include computations. I would say the main challenge we saw at the time when we were working on the Safeware program, so that was from 2015 to 2019, is the efficiency of attribute-based encryption as compared to, let's say, FHE or proxy encryption. But I see it as a future technology, advanced technology that we can certainly leverage.
That's great. And one of the great features of OpenFHE is the key splitting, where you can actually split the key like a Shamir type key split, and then you can perform multi-party computation on the ciphertext. I assume in things like signatures that's possible. What application area do you think that this would be most useful in?
It's actually the specific flavor that OpenFHE focuses on is threshold FHE. And the idea there is that each party may have a share of a secret key. No one ever sees the secret key. And the good, I would say, property that this threshold FHE has is that in these scenarios, only key generation and decryption need to be distributed. The computation itself can be done the same way as a classical single key FHE. So this is something that the library supports, and we actually even used in some scenarios in Duality. The advantage is, I would say, the primary advantage is when we have multiple data owners or multiple parties involved. And we want to make sure that a single party cannot decrypt the result, that only in coordination they can decrypt it. This threshold method gives that ability, extra control. To perform this, so in scenarios with collaboration, I see it as a necessary feature often. There's also an interesting efficiency side effect. When we have access to threshold FHE, we can do bootstrapping much cheaper. So the bootstrapping can be done in also a distributed manner, and in this case, it's a operation that's comparable in complexity to encryption. So this is just another. And those features are available in OpenFHE to play with.
Yeah, and obviously with post-quantum cryptography, we've been through all these rounds, and lattice cryptography comes out as the best encryption, key encapsulation. I keep saying key exchange now. It's not that. It's key encapsulation, and also for digital signatures. And most of the methods have proofs of security, but obviously there's still a worry about landing with errors, that maybe tomorrow someone might publish a paper that breaks landing with errors. So, and I know that NIST is quite keen to find alternatives in the post-quantum cryptography space, isogenies and multivariate cryptography and things like that, McAleese, which creates massive keys. And we've also got Sphinx Plus, which is a hash-based Merkle approach. So to have an alternative is really important. And this is a really difficult question to ask you, but what do you think might be, is there any contenders to lattice and homomorphic, fully homomorphic encryption at the current time, or what might come along to give us an alternative?
Yeah, at the moment, lattice-based cryptography is the only feasible and practical solution. That's and this is why a lot of NIST efforts are effectively converging to using lattice-based cryptography. So at this time, it certainly looks this way. It is hard to predict what may happen in the future. So it's very possible that some cryptographers may come up with a very different formulation. And for instance, a topic that has been of interest for many theorists, and I remember invited a talk by Zvika Brakersky on this as well, is related to finding some other solutions, for example, the ones that do not require noise. So noise is something that's inherently needed in any of the lattice problems we're dealing with, and this creates an efficiency problem we have to solve. If one could find a noiseless, computationally hard problem with similar capabilities and post-quantum properties, because there are some proposals, but they're not post-quantum. That's a, I would say, open topic of research. We never know. Just like with Craig Gentry's work, it was hard to say at the end of 2008 that we would have a FHE scheme. Maybe tomorrow, who knows?
Yeah.
Maybe we won't see something for a while.
Yeah. And I suppose organizations need to look at what their application is. And if it's adding and subtracting, then Paleo is fine. And there is partially homomorphic encryption that can be used. And I think there's even columnar encryption models, which is using symmetric key type methods there. So I think a lot of it depends on the application domain, but the dream would be for fully homomorphic encryption, hopefully with an alternative method just in case it breaks. So what does the next decade look like in cryptography? What are the key problems that need to be solved?
Yeah, so I would say, I mean, of course, there are still a lot of problems with FHE, so the area that we're working in. There are a lot of problems created, or I would say problems that became more pronounced due to the Gen AI and the use of essentially various technologies like ChatGPT to explore all the data that's out there. And with the ability to analyze massive amounts of data, several privacy questions come up. One is when this data is being analyzed, how to achieve privacy of that data. Some of the questions are directly related to the Gen AI models. Well, maybe those models can leak some information about something about the data that was used to generate those models. So there are a lot of questions certainly that will be, in my mind, associated with the privacy of AI, and where I mean, FHE is one of the solutions. Maybe there will be some, again, multiple crypto problems, and maybe somewhat related to this is, in my mind, is the problem of data scale. So we've observed over the last decades very high inflation rate, I mean, of the data. The data keeps growing, and we often get into, let's say, even I'll use FHE as an example, scalability problems. Okay, we know how to solve a problem. We can know how to maybe do and compute a certain even deep computation circuit, but to do it for billions or trillions, or I mean, I don't know, of data points, that's very challenging. So this is how to achieve privacy for this massive amounts of data, considering that we are getting into these Gen AI technologies and so on that feed from this data. I think, in my mind, these are going to be the biggest problems that we'll be facing, and solutions to those problems is what we should focus on, at least from the practical perspective.
Yeah. Obviously, a big disruption is going to be with post-quantum cryptography. We'll have to replace all our existing public key encryption, all our key exchange methods, and that's going to have a massive impact. I know that in the US, Biden has signed off a memorandum to protect or to seek out all public key entities within critical national infrastructure, which will include healthcare, energy, transport, and so on. So, how do you see this panning out? I mean, how do we move to this quantum? Is there a switch that we just flick, or is there an intermediate state that we get into?
It's yeah, it's an interesting one. So we do know that many currently used methods based on discrete log problem or factorization problems are not immune or not resilient to quantum attacks. It's not always clear how close the current quantum computer capabilities are to solving them these problems in a practical setting. Although we do see a lot of motivation by top companies like I don't know Google and so on, IBM, and many even startups working in this area. So it's a little bit hard. I think a major trigger can be when some practical secure setting based on discrete log or factorization is actually solved with a quantum computer. I see it as a discrete step that like at this time in practical setting, especially let's say maybe government is more concerned about this, but let's say non-government sectors. Okay, I mean, it's not a problem, it's a hypothetical problem.
Yeah,
Until it becomes a practical problem, we're fine. But as soon
yeah,
as something does happen, like there is an advance in quantum computing, that may basically speed things up and may trigger. Yeah, I see it. Most likely, it's going to be this discrete jump at some point. Of course, there will be attempts, and there are attempts to prepare for it. And again, the government is more concerned because they're trying to look into the future. But for enterprises, for other for commercial entities, I feel it's going to be like another year 2000 scare or something like that.
yeah.
That's how I see it.
Yeah, I suppose a lot of it is regulations and auditing and things like that.
True.
When you're
That
looking
might be
ahead
another trigger.
5 to 10 years, the EU might mandate that at least critical national infrastructure in the EU has some mitigation strategy, and especially if the data is kept for more than 10 years or so. Blockchain obviously will cause a problem because we need to make sure it's safe forever. It can't just be safe just for today. So you've had such a varied career. It's unbelievable the steps that you've taken and all of the degrees and the PhD that you took. If there's one thing you could have changed in your career, what would it have been?
Uh, you know what? I mean, I cannot think of anything honestly. I mean, I know it's been a very interesting path, including immigration and changing from, I mean, across different disciplines. But it's been interesting. It's I'm always looking forward to exploring something new. So even if some attempts were not successful, I mean, I learned from them. So uh, I, yeah, I don't have any regrets. I feel like
Yeah.
I would just follow the same path.
It's really great. And it's always nice if you get to a point in your career where you're happy and everything that you've done, the mistakes you've made, the good choices that you've made, you sit back and you don't actually regret anything and you're happy where you actually are. So that's great. So my penultimate question is what advice would you give to graduates? Obviously, you've seen education, you've seen industry. What advice would you give graduates who are near to graduation about the skills and knowledge that they really need in this world that's evolving?
Sure. Yes. So I would, for me, it's always been important and to be open-minded to teach yourself how to do self-study, to be open to exploring new fields, not to have a narrow thinking. It's always good to explore and look across multiple disciplines. So it's even when I work as a professor and teaching graduate students, my goal was I never had tests with memorization or something like that. It's always was open laptop, open everything, but the problems were not simple. And it's I think the problem solving skills, being open to exploring, rather than having a narrow skill set in a certain domain, because that skill set might not be relevant tomorrow, for instance, or something may change. I think is very important. So this is always, I think, always exploring new things, going beyond the comfort zone. I always suggest that.
Yeah. Why is the sky blue? Be like a child and look at things and find things that aren't working and try to solve them. I think it's really important as a researcher to do that. And so if you were a new researcher, brand new, which problem would you address just now? It doesn't have to be cryptography. What problem would you like to solve with research?
It's a very interesting question. So, like, I'm certainly intrigued by the major steps in, let's say, Gen AI and the scale at which this field has been advancing. So, I'm even I sometimes touch with Gen AI advances as an application domain, but this field is very, very interesting. So. Uh, of course, it's as a researcher, that's an interesting field. Of course, sometimes I have ethical concerns about how it's advancing too. So there is a little bit of caution here, is not to get too much carried away by research, because this can become a dangerous weapon if used for some other purposes. Then so yeah, my personal, yeah, I would say I'm excited about the progress in AI at this moment, and I find it interesting. So this, if I were to, let's say, of course, FHE is interesting and cryptography is interesting, but this is the field that I would
Mhm. Yeah,
be intrigued by as a researcher, and I
yeah,
suggest
yeah.
studying.
I think if you drew a Venn diagram with AI and cryptography, the bit that they meet is the bit that becomes really interesting and that you're trying to now look at how you protect. I think it's been an open market for using citizen data, and it needs to stop. And citizens need to have control of their data, the rights to take it back when it's been used, and consent becomes a core word in that. And I think cryptography and AI together should build a better world, especially if we can create the hardware computation to actually support the polynomials and so on. So thank you very much for all your work on OpenFHE. I've really enjoyed implementing with it, and all our researchers are now working with it, building real applications for real people. And we think there's an amazing future ahead. And really, every single day, as you said, you've just published a paper that I can now read. And I think that's what I find exciting in this area, that tomorrow I'll pick up a paper and it'll completely change my viewpoint on something. And the toolkit you've created is amazing. It's the Lego blocks for building a new, trusted, resilient, privacy-aware world. And I think it's up to us to take your building blocks and actually build the future. We've had 50 years of the Wild West with the internet, and now's the time to rebuild it again. And I think all the cryptography that was created 20, 30 years ago is now coming alive now. So thank you so much for your work, and really appreciate you spending the time, taking out your busy day. And hopefully if you come, where are you in the world just now? Which place?
I'm in New Jersey, so I'm
In New
actually
Jersey,
my
in
home
New
in New Jersey.
York. Yeah, it's a beautiful place. Well, I'm in Edinburgh just now, and if you're across in the UK, it'd be great to host you here, and maybe you can give a guest talk to our students or at one of our conferences. So thank you so much, and keep up the great work and your great passion in what you do. I think open source software is the right way to do these things. When we built the internet, we built them with RFCs and things that were open. We didn't have the close standards of the past with IEEE and ISO and OSI and so on. We built in an open way that allowed everybody to interact and understand. So I think the way that you're building open source is very unselfish, and well done for that, and all the best for the future. Okay, thank you.
Thank you. I appreciate the opportunity. It was a pleasure talking to you, and would be happy to visit.
Good. That's good. Thank you.
Thank you.